All right, welcome to 3.7. We're going to start by talking about a very important question. What are inverse functions? All right. So my claim is that you've been using inverse functions for a long time. All right. So the whole idea about inverse functions, the inverse functions undo other functions. So we've been doing this for a long time. Let's say you're solving an equation, right? You're solving an equation and you have something like this. What do we do to solve this equation? We use an inverse function. X is getting multiplied by 2. How do we undo that? Well, actually, usually we'll think about it as dividing both sides of the equation by 2. We're applying an inverse function to both sides. Right? Let's say we're solving an equation. We have something like this. What do? Well, we subtract 5 from both sides. We apply what is happening to x. X is being added by 5. We are inversing it by subtracting both sides by 5. We do inverse functions all the time. Cubed root x cubed equals 8. Well, let's use an inverse function. Take the inverse function of both sides. This is what inverse functions are. They're ways of undoing functions. I've got an x cubed. I don't want an x cubed anymore. I just want an x. And in every single one of these situations, right, the result is that this left-hand side, they cancel out, and we're just left with an x, right? These cancel out, and we're just left with an x. These cancel out, and we're just left with an x. That's what inverse functions are all about. Undoing things, just leaving us with what we started with, that x. So let's kind of look at a definition over here. All right. Definition. If f of g, oh no, not function composition, it's back. Right? That's why we learned about function composition, so we could use it in the future. We're learning about inverse functions. Guess what? We're going to use that in the future too. So if there's an f there, if f of g of x equals x, and that's very important, g of f of x also equals x. So it doesn't matter which way we compose these functions. If we do g first and then f, or f first and then g, if the result is that these functions cancel out and we're just left with x, just like over here, then f and g are inverse functions, or inverses of each other. All right. And another way of writing that, we'd say that g of x is the inverse function of f. This right here is called f inverse. That's how we say it. And it's not a negative exponent, right? Like another note, another warning, right? F inverse of x is not the same as 1 over f of x. That's how negative exponents usually work, but this is not an exponent. It's a little weird. It's kind of garbage notation, honestly. I don't know who made this up, but whoever it is, shame on you. It's not consistent with other areas of mathematics, so just watch out for that. That's kind of what we got going on here. And if you're curious what I mean by negative exponent, it's stuff like, if I did have something like 2 to the negative second power, that negative in the exponent gives us a reciprocal. This simplifies to 1/4, stuff like that. Negative exponents. Anyway, so that's inverse functions. This is our definition. This is what we're going to use. Let's use it now. Example 1. You know what? Let's do example 1 on the next page so it fits. Example 1. Verify that f and g are inverses. Part A, f of x equals the cubed root of x plus 1, and g of x equals x minus 1 cubed. Let's tie multiple topics together. Before we even start this question, let's think about function transformations. These are both toolkit functions, right? The cubed root of x looks like this. X cubed looks like this. This is a plus 1 on the outside. That's a vertical shift up 1. This is minus 1 on the inside. That's a horizontal shift right 1. Just connecting topics. So in order to do this, verify that they're inverses. We're going to use the definition. This is what we need. Okay? We need to check, right? Is f composed with g equal to x, and is g composed with f equal to x? There are situations where only one of these is true. We need to make sure they're both true. So you strap your 3.4 hat on, function compositions, and you evaluate what is f of g of x. You evaluate what is g of f of x. And this is what we hope it simplifies down to. All right, that's a little extreme. So f of g, function composition, just means f of g of x, like so. Now we say, what is g of x? G of x is x minus 1 cubed. So replace it. It's x minus 1 cubed. That's what g of x equals, so replace it. Right? This red thing and this red thing are the exact same thing according to this rule. That's the definition of g of x. And now what we need to do, right? This is our input. We're plugging it into x. Sorry, we're plugging it into f. So look at f. Replace all the little x's with x minus 1 cubes. So normally this is what f is with a little x right here. But we're not plugging in x anymore. We're plugging in x minus 1 cubed. Now be very careful here. We do have some cancellation. The exponent cancels with the whole radical. It's not just the 3's that cancel. It's the exponent of 3 with the cubed root. This cubed root is one thing. So it doesn't become a square root or anything. Okay? So this does just cancel to become x minus 1. Oh, we don't need parentheses here. Oh, great. Minus 1 plus 1 cancels out. When I apply both of these functions to any number, this could be anything. This could have been 2, this could have been 5, any number x, and I apply both of these functions, I get that same number out. Any x, this will be true for. Now, real quick, let's just check it on the other side. G of f of x. We say, what is f of x? F of x is this. Replace it. Cubed root of x plus 1. Excuse me. Now we're plugging this into g. So what we do, right, is we say g is normally x minus 1 cubed. Instead of x, we're putting in the cubed root of x plus 1. I didn't give myself quite enough room there. And now, just like before, right, these plus 1 minus 1s cancel. We're left with the cubed root of x cubed. Oh, and again, those cancel, right? Cubed and cubed root all cancel together. We're just left with x. These are the two things that we wanted to show. We verified it. F and G are inverses. Ta-da! And that's basically this whole video. I'll do one more example problem if you want. just shows like some more complicated algebra, but there's nothing new in it. So you can be done with this video if you want. Or a bonus question. Verify that these two functions are inverses now. F of x equals x over 2 plus x, and g of x equals 2x over 1 minus x. These are both variations on the reciprocal function, I believe, but it's a little bit more complicated. But I'm pretty sure they are. You'd have to use long division here to really see how there are variations of the reciprocal function. And I'm not going to do long divisions of binomials right now. Anyway, let's verify. We need to check, is f of g of x equal to x? And do g and f composed in this way cancel each other out and just leave us with x as well? So we approach it with the same logic. This is just going to have more complicated algebra to simplify. The g of x, right, is just 2x over 1 minus x, right? These two red underlined things are the same thing because it tells us what g of x is right here. And then what we need to do is we need to plug this into f. All right, so everywhere in f that there's an x, we're replacing here and here, we're replacing with that inside. 2x over 1 minus x, 2x over 1 minus x. Now this is where things get a little tricky. This is a complex fraction. Complex fraction means there are fractions inside of fractions. And to simplify these, we multiply by the least common denominator. The least common denominator is 1 minus x. Let's multiply by 1 minus x divided by 1 minus x. And it can help sometimes to think of it as 1 minus x over 1. So we're multiplying by the LCD over 1 on the top and the bottom. Because now look what happens. When we multiply these across, we have a 1 minus x on top and a 1 minus x on the bottom. We're just left with a 2x on the top. Oops, wrong color. This is what I said when I mentioned this problem just has more messy algebra. And on the bottom, we actually have to distribute. So the first one is going to be 2 times 1 minus x. And the second one, okay, the second one's going to cancel again. Right, the 1 minus x's cancel in that second product. You can do it off to the side if you want to see where that comes from. Be very careful. We cannot cancel here, right? This does not cancel because there's addition and subtraction. You can only cancel once everything is combined and factored. We can't cancel here. Can't cancel until it's fully simplified. Right? There are like terms here that we haven't dealt with yet, and we need to. So, oh dear, we're not going to have enough room for this. Here, we're just going off the board. So this is going to be 2x divided by, if we distribute, right, that's going to be 2 minus 2x. And then plus a 2x. Ah. Now those 2x's cancel. Minus 2 plus 2x combine like terms. What do we have after that? 2x divided by 2. Ooh, this is starting to look nice. Now these 2's cancel. What are we left with? We're just left with x. That's exactly what we wanted to be left with. Right? We wanted to show that these two functions completely undo each other and that no matter what our input is, no matter what x our input is, the output is that same input. So I'd recommend you take a moment, pause the video, try to use these algebra tips to simplify the other one. And then I'll work through it and we'll see if we get the same thing. So the definition of function composition is g of f of x And f of x is x over 2 plus x. Plug that into g. So g is 2x divided by 1 minus x. We're not using x's anymore. We're using this input, like so. And now we have to simplify it. Before multiplying by the LCD here, let's simplify this top. That numerator is going to be 2x over 2 plus x. And the denominator is going to be unchanged for now. And now let's multiply by the LCD on the top and the bottom, which is going to be 2 plus x over 1 and 2 plus x over 1. On the top, they just straight up cancel, and we're just left with 2x. On the bottom, we have to distribute. They cancel in one of them, but the other one is just going to be 1 times 2 plus x. But it does cancel on the other one. Now plus x and minus x are going to cancel, which is going to lead us to just 2x over 2. And then just like before, the 2's cancel. And again, we are just left with x, exactly what we wanted. So our conclusion is f and g. Nope, that's not how you write and. F and g are inverses. I do another one of these in the selected homework problems video. So check out that later video if you want to see me do more of them. Okay? That's this video. Good luck. Let me know if you have any questions.